Look through the window in front of you. It is perfectly clear, seemingly empty space, yet it is solid enough to keep out the wind and rain. Glass is so fundamental to modern life, from the screens in our pockets to the lenses in our eyes, that we often forget how strange it actually is. If you look at it under a microscope, you won't find the neat, repeating patterns of a typical solid. Instead, you find a chaotic, frozen mess. It shouldn't be solid, yet it is. To understand the mystery, we have to look at how atoms behave. In a typical solid, like salt or ice, the atoms are arranged in a perfect, repeating lattice called a crystal. This structure is stable and predictable. In a liquid, like water, the atoms are moving around constantly, jostling and sliding past one another in a disorganized swarm. When most liquids cool down, they reach a freezing point where they suddenly snap into that neat crystal lattice. But glass doesn't do that. It misses the cue. When molten glass cools, the atoms begin to slow down, just like any other liquid. However, glass is usually made of complex molecules or cooled so quickly that the atoms don't have time to find their proper places in a crystal grid. As the temperature drops, the liquid becomes increasingly viscous, thick, like honey, then like tar. Eventually, it becomes so thick that the atoms simply stop moving. They are locked in place, frozen in their chaotic, liquid-like positions. This is the glass transition, a process that physicists still struggle to fully define. This state of matter is known as an amorphous solid. It has the mechanical rigidity of a crystal but the disordered internal structure of a liquid. This creates a paradox. Because there is no grain or crystalline boundary for light to bounce off of, the material can be perfectly transparent. If glass were a traditional crystal, the boundaries between the tiny crystal grains would scatter light, making the material opaque or milky. By staying messy on the inside, glass allows us to see clearly through to the outside world. Nature discovered this impossible material long before humans did. Obsidian, a dark and volcanic glass, forms when lava cools so rapidly that crystals cannot grow. Early humans prized obsidian for its ability to break into incredibly sharp, thin edges far sharper than any metal blade. Even today, some specialized surgical scalpels use obsidian blades because they can be sharpened to a near molecular level. It was our first encounter with a material that didn't follow the rules of stones or metals, acting as a bridge between the organic and the geologic. For centuries, humans refined the process of making glass by melting sand with soda and lime. The goal was always clarity. In the workshops of Roman artisans and later the masters of Venice, glass was transformed from a cloudy curiosity into a medium for art and science. By controlling the impurities within the chaotic atomic structure, we learned to bend light. This led to the invention of spectacles, microscopes, and telescopes, effectively doubling the human lifespan of productivity and expanding our vision to the farthest reaches of the galaxy. Today, the most critical application of glass isn't something we look through, but something that carries our data. Fiber optic cables are strands of ultra-pure glass, thinner than a human hair. Because glass is an amorphous solid, we can pull it into long, continuous threads without the structural weaknesses found in crystals. These threads use total internal reflection to carry pulses of light across oceans in milliseconds. Our entire global communication network is built on the back of this frozen liquid, transporting information at the speed of light through tubes of sand. But we are now pushing glass beyond transparency. Scientists are developing metallic glasses, alloys of metals like zirconium or palladium that are cooled so quickly they retain an amorphous structure. Unlike traditional metals, which have crystalline defects that allow them to dent or bend, metallic glass has no such weaknesses. It is incredibly strong, elastic, and resistant to corrosion. Imagine a smartphone casing that never scratches or a surgical implant that never wears down. We are taking the messy physics of glass and applying it to the strongest materials we know. One of the most exciting uses for these new glasses is in deep space. Traditional lubricants freeze or evaporate in the vacuum of space, causing metal gears to grind and seize. However, gears made of metallic glass can operate at extremely low temperatures without any lubrication at all. They are being tested for use in planetary rovers and satellites. By utilizing a material that exists in a permanent state of transition, we are building machines that can survive the harshest environments in the known universe where traditional solids would simply fail. Glass remains one of the great unsolved problems in condensed matter physics. We know how to make it, and we know how to use it, but we still don't fully understand why the glass transition happens the way it does. It is a reminder that even the most common objects in our lives can harbor deep scientific mysteries. The next time you look through a window or tap a screen, remember that you are interacting with a material that defies the simple categories of liquid and solid, a transparent miracle of chaos frozen in time.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.